Question number 7. A vertical slender rod is suspended by a hinge at the top and hangs freely. It is heated until it attains a uniform temperature of T. Neglecting the effect of gravity, the rod has, for example, this is hinge support and this is a rod, slender rod is suspended, which is heated by a temperature uniformly. So what will happen? We know that the thermal strain, for example, this is the length of the rod. So because of heating, there is a strain. So there will be strain, which is nothing but alpha delta T. Delta T is the temperature difference. For example, if the rod initially was at 10 Kelvin temperature, now the temperature is increased by uniformly heating to a final temperature of 50 Kelvin. So delta T will be equal to TF minus T initial. So here is 40 Kelvin, which is the difference in the initial and the final temperature. Alpha is the coefficient of linear expansion. Delta is the temperature difference. And this is the longitudinal strain. So when we are heating uniformly, then delta L will be equal to the change in length. For example, the rod will extend or elongate by amount of delta T. This constant is usually positive and length is given. If delta T, the temperature difference, is positive, then the length will increase. If delta T is negative, then the change in length is negative, means the length of the bar will decrease. So we can see that there is a strain will produce. Delta L by L will be some value not equal to 0. But as there is free expansion, rod is allowed to expand freely. So there will be no stress. Stress will be equal to 0. Why? Because we can say, somebody will say, if there is a strain, why not a stress? Here we don't have to apply the Hooke's law, stress directly proportional to strain. This is not valid for thermal strain cases. For clearly understanding this, what is stress? Stress is force per unit area. This force is the resisting force. If you are allowing a rod by heating, it will expand freely. So there is no resistance to their expansion. Hence, there will be no resistive force developed in the material. Hence, the stress will be equal to 0. So there will be a strain, but stress will be equal to 0 in case of thermal strain. Question number 13. A thin rectangular plate which is made up of isotropic material which satisfy the von Mises failure criteria. The failure criterion has yield stress or the failure stress of 200 megapascal, and this plate is subjected to 150 megapascal in x direction. We have to find what is the value of sigma y, stress in y direction, to satisfy the von Mises failure criteria. This is two-dimensional stress case and there is no shear stress acting on the plate. So we know the failure criteria for two-dimensional state of stress is sigma 1 square, sigma 2 square minus sigma 1, sigma 2 less than equal to sigma failure square. Okay. Sigma 1 and sigma 2 are the principal stresses. Principal stress, we know that sigma x by plus sigma y by 2 plus 1 by 2 square root sigma x minus sigma y whole square plus there is no shear stress, so 0. So sigma 1 will come sigma x. Similarly, sigma 2, by using negative sign for sigma 2, we will get sigma 2 equal to sigma y. Now we have to put value of sigma 1, sigma 2 and sigma 1 into this equation to find the value of sigma y. Here sigma x is given 150 megapascal whole square plus sigma y square minus 150 sigma y. We are putting just the value of sigma 1 and sigma 2 into this equation equal to 200 whole square. Solving this equation, we will get the value of sigma y. We will get two values. One will be 227 megapascal and second value minus 77 megapascal. From the given options, the positive value of 227 megapascal is right. So the answer A will be the correct answer. Question number 16. A column of length L, flexural rigidity is given EI with a boundary condition of one end fixed and other are hinged. We have to tell the critical buckling load for this type of column with boundary condition fixed end and hinged end. We know that Euler buckling load is pi square E I upon L square effective length. If the length of this column is L, for this type of boundary condition, the effective length will be equal to 0.7 L. So the buckling load will be equal to EI on 0.7 L whole square. Option B is correct, or we can also write this 2 pi square E pi upon L square approximately. This option will be correct, option B. Question number 27. 2D state of stress is given sigma xx, sigma yy, tau xy. Normal stress in x direction and the y direction and the shear stress in xy plane with no body forces. We have to check they satisfy the equation of equilibrium and compatibility equation or not. Equation of equilibrium is given by partial differentiation of normal stress with respect to x plus partial differentiation of shear stress with respect to y. As there is no body force, So these will equal to be 0. And partial differentiation of normal stress along y direction with respect to y plus tau xy with respect to x equal to 0. If these conditions satisfy, then the state of stress satisfies the equation of equilibrium. Let's check. Putting the value of sigma x and tau xy in equation first. For the equation of equilibrium, we will get 6xy, this will be 0, minus with respect to y 6xy, this will be 0. So equation first is satisfied. Now we will check another equation, which is y cube plus 14xy plus partial differentiation of tau xy with respect to x three y square plus 14x minus 3y square minus 14x, then this also becomes 0. So equation of equilibrium is satisfied. Equation of compatibility for two-dimensional state of stress is given by this. That's square del square by del y square. Now we are adding sigma xx plus sigma yy. Now we are multiplying these terms by the terms in the bracket. This will be here, and this multiplied by this is given here. Now we have to solve this equation by differentiating partially with respect to x 2 times and here with respect to y. After differentiating the equations for a single time, we will get 6xy plus 14y and 3x square plus 8y plus 3y square plus 14x. Now we have to again differentiate partially with respect to x here and here y. We will get 6y plus this will be 0, this will be 0, 8 plus 6y, this will be 0. So this will not be equal to 0. Hence the equation of compatibility is not satisfied and equation of equilibrium is satisfied for the given state of stress. So option A will be the correct answer. Question number 28. A uniform cross-sectional rigid rod of mass m of length L is hinged at one point at the upper end and suspending like a pendulum. We have to find the natural frequency for the small oscillation. When the rod is in such a position, we know that the CG will lie at the midpoint of the rod at L by 2. If the length of the rod is L, then CG will be at L by 2. Now we are taking the component of its weight, which is m into g. In this direction, w sin theta, mg sin theta. So there will be a restoring torque produced by the component of its weight. So the equation of motion will be equal to mass moment of inertia of the rod plus angular acceleration plus W sine theta multiply by this length L by 2 equal to 0, as there is no other force acting and other forces are neglected. So this will be equal to mg L by 2 sine theta divided by I equal to 0. As the oscillation is small, theta is small, so sine theta approximately equal to theta. So this will be equal to L by 2 I theta. Here the equation is non-linear because sine theta can be expanded. And now after assuming the small oscillation, this equation becomes linear. We know that natural frequency will be equal to square root of this term mg L 2I. The mass moment of inertia of rod is nothing but equal to m L square by 3. Putting the value of I in this equation, we will get mgl by 2 ml square 3 square root. After solving, we get 2L. This will be the right answer. Option D is correct. Question number 29. A thin rectangular plate is given which is subjected to two-dimensional state of stress tau naught, which is in plane shear stress, and sigma y, which is equal to sigma naught. There is no normal stress in x direction. These values are given. Tau xy is equal to tau naught, sigma x is 0, sigma y equal to sigma naught. You have to choose the correct Aerospace stress function. Aerospace stress function is denoted by phi. For getting the normal stress in x direction, we have to partially differentiate the Aerospace stress function with respect to y 2 times. Similarly, sigma y, normal stress in y direction, we have to differentiate partially Aerospace stress function with respect to x 2 times, and tau xy is given by this. So for solving this question, to satisfy this state of stress, we have to use our mind. As we know that sigma x is 0, so we have to choose a function which cannot be differentiated 2 times because sigma x is equal to 0. So for example, if we are choosing this option, then we can differentiate this function more than 2 times. So there will be some value of sigma x. But according to the question, sigma x is 0. So this option is wrong. Similarly, this equation can be differentiated more than 2 times. So we will get some value of sigma x. But in the given question, sigma x is 0. So this and this option is wrong. Now we have to check whether B option and C option is correct or not. As we can see in the option B and C, there are no y terms with multiple power or the higher order. So when we are differentiating this, sigma x will become 0 for both the option. So this option and this option, one of the option will be the right. Now we have to check this, as sigma y is equal to sigma naught. Now if we differentiate partially this equation with respect to x 2 times, we will get minus sigma naught. So this option is wrong. So final, this answer is right. We don't have to solve actually, we just have to use our brain to solve these tricky questions. Question 32. During an undamped oscillation of single degree of freedom, a time and displacement plot is given in which the third peak of magnitude of 100 and the 10th peak of magnitude of 10. We have to find the damping ratio. From the third peak to 10th peak there are 7 cycles. We know the formula of logarithmic decrement, which is denoted by del equal to 1 by n ln x1 upon xn plus 1. Here x1 is the 100 and xn plus 1 is 10. 1 by 7 ln, this is the third peak, x3, and x7 plus 3 equal to 10. So 1 by 7 ln third peak and 10th peak amplitude or magnitude. 1 by 7 ln 100 divided by 10, we will get 0.32894. This is the value of logarithmic decrement, and there is another formula for logarithmic decrement is 2 pi e square root 1 minus e square. E is the damping ratio. By using this formula we can solve. We will get value of E equal to 0.052. So option A will be the correct answer. In question number 48, a beam is given with the type of loading, and we have to find the bending moment diagram for this given case. For that, we will assume RA be the reaction at the support A and RB the reaction at support B, and this bracket is given at the center of this beam, so the distance will be L by 2, and here also L by 2. So we are solving this by superimposing the resultant force and moment due to this load P at the center. This force P will produce a anti-clockwise moment about point C, which will be equal to P into A. P into A, and this force is superimposed at the point C. A, B. Now we have to find the reactions. We can use the equation of static equilibrium for finding the equation. Summation of all the forces, vertical forces, equal to 0. So RA plus RB will be equal to load P, and we are taking the summation of moment about point A equal to 0, which is hinge point. So minus RB L, this is anti-clockwise, so we are taking anti-clockwise negative and clockwise positive, and the force, vertical force, positive, downward negative. This force will produce a moment about point A, clockwise, P into L by 2 equal to 0. Putting the value of A, which is equal to L by 10. After solving the equation, we will get the value of RB equal to 2 by 5 P. Putting these value into equation, first RA will be equal to 2P by 5, 3P by 5. So we will have the values of RA and RB. Now we have to find the bending moment diagram. RA, which 3P by 5, RB 2P by 5, and this is the loading. Now we have to find the bending moment diagram, A, B and C. Okay. The force or reaction force at A will produce a bending moment about point C, which is equal to 3P by 5 into this distance L by 2. This will be equal to 0.3 PL up to point C. But as we know, there is an anti-clockwise moment is acting at point C already, opposite to the moment that is produced by the reaction support. So this will become negative 0.3 PL minus 0.1 PL, which it is equal to 0.1 PL. So the moment at point C will become 0.2 PL. At the point B, the moment will become 0. Here at point B, there is a roller support. Roller also does not resist any moment, so the bending moment diagram will look like this. So option C will be the correct answer. In question number 49, we have to find the maximum value of the shear stress. The loading was given in the question 48. RA is the reaction at the support A and RB is the reaction at support B. We have calculated these values. We know the formula for the shear stress, maximum shear stress in the case of the rectangular section, which is given by 3 by 2, V by A. V is the shear force, A is the cross section area. So for maximum shear stress, maximum value of shear force will be used. For that, we will draw shear force diagram. At A, there is a 3P by 5 up to C, it remains constant, and at C there is a point load of P in the opposite direction, so it will become 0.4 in the negative axis. Here it is positive, negative 0.4 P, which remains constant, and then become this at point B. So this will be the shear force diagram. Maximum shear force will be, we can see this is the maximum shear force, so we will use this as a value of V. So shear stress will be equal to 3 by 2 maximum shear stress into 3p by 5 into 1 by area, which is nothing but h into h square. So maximum shear stress will equal to 9 by 10 p by h square. So we will get the value of 0.9 p divided by h square. So option D will be the correct answer.